Hello, welcome. In this short video, let us look at an example illustrating the indirect influence of a magnetic field on a couple of springs suspended from an electric circuit. So consider the following electric circuit. We have a resistor with resistance equal to 4 ohms and a voltage source with voltage equal to 12 volts, a DC voltage source, and then this source is connected to a couple of springs on both sides, and these springs are in turn connected to a wire of length 10 centimeters. So this is a wire, and this wire has a mass equal to 5 grams. And this wire is in turn surrounded by a magnetic field. Now our goal is to study the indirect influence of this magnetic field on the springs. So other piece of information is the initial stretch on the springs is given by d naught is equal to 0.2 centimeters. That is the stretch on the springs due to the weight of the wire alone. That is, when the magnetic field is turned off, the springs are still stretched. When the magnetic field is turned off, the springs are stretched by the weight of the wire, and this stretch is equal to 0.2 centimeters. When the magnetic field is turned on, then the stretch is equal to, an additional stretch is equal to 0.5 centimeters. When the magnetic field is turned on, there is an additional stretch on the springs which is equal to 0.5 centimeters. And we already know that the wire length is given to be 10 centimeters. And we have the mass of the wire equal to 5 grams. So the goal of the problem is to find the magnitude of the magnetic field flux density. Designated by the letter B. So this is the goal. So the first step is to use the formula for a force on the spring, that is F equal to the spring constant K multiplied by the stretch d naught. That is, when the magnetic field is turned off, this is the equation for the force. So this is equation 1. This is force on a spring. And this force is balanced by weight of the wire, which is equal to m into g, where g is the acceleration due to earth. So since there are two springs, the force acting on each spring should be equal to half of this weight. So F should be equal to half of mg, which is in turn equal to k into d naught. By using this equation, we can find that the constant k is equal to m into g by 2 times d naught, which is equal to 5 into 10 power minus 3, that is the mass, into 9.8 over 2 times, and d naught is given by 0.2 centimeters. Therefore, upon simple calculation, k should be equal to 12.25 newtons per meter. Now, the magnetic field B is turned on. So because of the magnetic field, there is an additional stretch FAD is equal to the spring constant K into the stretch D1, where D1 is equal to 0.5 centimeters, where D1 is given by 0.5 centimeters. Therefore, additional force on each spring is equal to 12.25 into 0.5 into 10 power minus 2. This is in newtons. So, the additional force on each spring is equal to 61.25 millinewtons. Therefore, the total force due to the magnetic field is equal to 2 times FAD, that is the additional force on each spring. So this is equal to 0.1225 newtons, because 2 times 61.25 millinewtons is 0.1225 newtons. So this is the force due to the magnetic field. And this force should be equal to the magnetic force. And the magnetic force on a wire of length L is given by I into L cross B, where L bar is the vector corresponding to the length of the wire and B bar is the magnetic flux density vector. and since the wire is suspended exactly perpendicular to the direction of the magnetic field, the magnitude of the force, the magnetic force, is given by I into magnitude of L into magnitude of B bar into sine theta. However, sine theta is clearly 1 because the wire is perpendicular to the magnetic field's direction. So this is equal to 1. Therefore, Fm should be equal to, that is, Fm is equal to magnitude of Fm bar, which is equal to I times magnitude of the length and the magnitude of the flux density B, and this is 1. And the current I in the circuit is clearly given by the ratio, the Ohm's law, which is voltage over the resistance. The voltage is given as 12 volts and the resistance is 4 ohms. So the current going through the circuit is clearly equal to 3 amps. 12 by 4 equal to 3 amps. So by equating this force to the force, the magnetic force here, we can clearly see that I into the length L into the magnetic flux density, the value of the magnetic flux density, that is the magnitude, this product should be equal to 0.1225, and therefore B is equal to 0.1225 divided by the current 3 amperes and the length given by 10 centimeters. So upon simplification, this should be equal to 408 millitesla. Thus, a magnetic flux density of magnitude 408 millitesla is required to produce an additional stretch of 0.5 centimeters in these springs. Thanks for watching.